Next feature we extracted from the cookie task is n-gram perplexity, which actually turned out to be our highest correlated feature with MMSE. We used two Nezernay smooth trigram language models, one built for controls and one for Alzheimer's, to explore whether or not the perplexity of a sample with respect to the two models is indicative of Alzheimer's disease. The benefit of n-grams is that they're language independent and simple to extract, meaning that a part-of-speech tagger or parser is not required. This means that we could run the same feature extraction on our German cookie data and our English cookie data. Additionally, prior work showed a correlation between Alzheimer's disease and a lower n-gram model of perplexity based on the works of Iris Murdoch, who was diagnosed late in her life with Alzheimer's. Here are the results we obtain on the cookie task. On the left, we have the normalized perplexity on the control model, and on the right, we have our normalized perplexity on the Alzheimer's model. Overall, we see that Alzheimer's participants, which are the red dots, have higher perplexities on both the control and Alzheimer's language models. This is contrary to the past finding on Iris Murdoch's work, but we take a different approach by building two different models. This means that Alzheimer's patients' language is less predictable, with higher variance. Also, this explains why the perplexity on CT feature that we saw earlier is significant, because the control model predicts the language of controls very well, but the Alzheimer's model doesn't predict either well. Now we're going to transition to the fluency task. The fluency task starts with the prompt, name as many animals or foods as you can in 1 minute. Here's an example response. As you can see, this prompt elicits a sequence of nouns, which is very unique. So we want to generate specific features for this task. So we wanted to come up with a notion of subcategory similarity to track the topic switching. The idea is to cluster relevant nouns for category naming tasks into subcategories via a semantic similarity score. And then we want to use these subcategories to generate features that quantify topic switching. So for the same example transcript as earlier, our ideal subcategory clusters would be fruit for apple, strawberry, and grapes, meat for veal and ham, vegetables for broccoli and asparagus, and sweets for ice cream and candy. This allows us to try to answer the question, are there significant differences in the logical ordering of items in the category naming tasks? And lets us use these subcategories as nodes for graph-like features, where the topic switches are edges between the nodes. To generate the subcategory clusters, we need some type of metric to quantify the similarity of two mentioned nouns. We use the Wu-Palmer pairwise similarity metric from WordNet, which is based on a notion of the least common subsumer, or the most specific concept, which is an ancestor of two nouns. So once again, given that example transcript, we would see that higher pairwise similarities should be grouped together in clusters. For example, apple and strawberry probably share the least common subsumer, fruit, and they would have a high pairwise similarity. However, for terms like ham and broccoli, they have a low pairwise similarity score, so these would actually probably be edges in the graph between two clusters. Here are the clustering results we obtained. This is a visualization of the clusters using PCA after doing affinity propagation, which also identifies an exemplar data point for each cluster, which is based on the similarity matrix obtained from all the nouns. We see that there are some very impressive resulting clusters, such as the pear cluster, which also contains apple, raisin, lemon, orange, grape, which are all fruits. But there are also some clusters with high variance in apparent similarities, such as this blue cluster, the bread cluster, which has pie, cabbage, potato, rice, sugar, and toast. So to fix this, we'd have to work with a different similarity metrics, most likely. Here are the features we extracted by going through each transcript and looking up the nouns used in the transcript with the generated clusters. Here we have a notion of relevance, which is a noun is relevant if it is included in the hyponym closure of the main category synset in WordNet, which means that if we had, like, in the food task, cabbage, we would expect cabbage to be a hyponym for food, but we wouldn't expect a noun like clown to be in the hyponym closure because that would be an irrelevant term. Using these clustered subcategories, we also generated graph-like features. Some general graph features are the number of nodes and the number of edges, where once again the number of nodes would be the unique subcategories and the number of edges would be topic switches between the categories. We also have measures of connectivity, which is the number of nodes in the largest strongly connected component and the number of nodes of the largest connected component. Additionally, we have measures of recurrence or repetition, such as the number of parallel edges, the average total degree of the graph, and the number of loops with 1, 2, and 3 nodes. We see that this is positively correlated with MMSE, meaning that healthy controls tend to mention more unique subcategories, and they also seem to switch more between topics. Finally, we looked at pause features of the cookie task, with the idea being that participants with Alzheimer's will tend to have more trouble with word finding than healthy controls. This manifests itself in filled and unfilled pauses. Filled pauses are a type of voiced hesitation. You probably heard a few of these during our talk already. These are simple to extract with a regular expression on the transcript. But we also wanted to extract the durations using forced alignments from Kaldi to give us more information. Also, we wanted to extract an acoustic feature, unfilled pauses, which are unvoiced segments within or between the utterances. So we also use the forced alignments from Kaldi. But we also label the start, inter-utterance, and intra-utterance pauses for the interviewer and participant by realigning the output from the forced alignment with the original transcript. Here are some results for the linguistic filled pause features. Here we see the number of filled pauses based on the regular expression in the transcript, and the acoustic and the duration from the forced alignments. Here are the unfilled pause features, which are generated from the acoustics and end up being very informative. We see that the negative correlation with MMSE shows that unfilled pauses are indicative of more severe Alzheimer's. We also would like to run this on the fluency, where we would expect large pauses in inter-utterance between the participant and intra-utterance in the participant as they pause between items such as different foods in the category naming task. I'm going to pass it back to Maria to sum up our features.